For 3.7 million years, the oldest human footprints outside Africa were preserved in volcanic ash at Latoli, Tanzania. They showed Australopithecines, early bipedal ancestors walking across a landscape in the aftermath of a volcanic eruption. Those prints were iconic, appearing in every textbook, every museum exhibit about human origins. Then, in May of 2013, after a spring storm battered the Norfolk coast, a geoarchaeologist named Martin Bates walked a beach at Happisburgh and noticed unusual depressions in the sediment, elongated hollows, patterns that looked familiar. He photographed them, uncertain. Back at his office, examining the images, he realized what he'd found. More footprints. Not from Australopithecines, from ancient humans. Nearly 900,000 years old. Preserved not in volcanic ash, but in estuarine mud. The oldest human footprints ever found in Europe. The oldest found outside Africa. And they shouldn't have existed because humans weren't supposed to be in Britain 900,000 years ago. The team had 2 weeks to document them before tidal erosion washed them away forever. Working in freezing rain during low tides, they used photogrammetry to create three-dimensional models. The prints showed a family, adults and children, walking together along a riverbank. 5 individuals. The smallest footprints belonged to a child, perhaps 3 years old. That detail, a child's foot, preserved for one fleeting moment across the millennia, makes what follows even more extraordinary. The question now facing archaeologists is profound. If humans were here, at the edge of the habitable world, nearly 1 million years ago, what does that tell us about human adaptability? About innovation? About survival? The site at Happisburgh continues to rewrite the story of human occupation in northern Europe. And with every tide, with every storm, more evidence emerges from the cliffs. The investigation is far from over. The village of Happisburgh sits on one of the fastest eroding coastlines in Britain. Every year, the sea claims another meter of land. Houses teeter on cliff edges. Sea defenses, long abandoned as too costly to maintain, crumble into the waves. For the villagers, this erosion is a disaster. For archaeologists, it's an opportunity, a window into deep time, opening wider with each passing storm. The cliffs here are part of the Cromer Forest Bed Formation, a complex series of river, estuary, and floodplain sediments that span over 1 million years of history. These deposits lie beneath the modern beach, normally protected by layers of sand and shingle. But when winter storms strip away that protective covering, the ancient world is revealed. Nick Ashton has been coming to this beach since 2005. He's a curator at the British Museum and lead archaeologist of the Ancient Human Occupation of Britain Project, AHOB for short. The project brought together specialists from the Natural History Museum, Queen Mary University of London, Royal Holloway, and Durham University. Their mission? To investigate when humans first reached Britain and how they survived. When Ashton's team first surveyed Happisburgh, they weren't expecting to find the oldest archaeological site in Northern Europe. They were following up on a chance discovery, a single hand axe found by a fossil collector in 1990. That axe suggested humans had been here at some point, but determining when would require painstaking excavation. The site is visible only at low tide. The team has a narrow window, perhaps 4 hours to excavate before the sea returns. The work is brutal. Winter temperatures, driving rain, wind that cuts through layers of clothing. The archaeologists dig in grid squares, removing sediment in controlled layers, screening everything through sieves. What they're looking for is subtle. Not bones, those rarely survive in these acidic sediments. Not structures, there are none. They're searching for flint, specifically, flint that shows signs of human working. In the ancient landscape of Happisburgh, flint was the most valuable resource. Hard, sharp when fractured, perfect for cutting. Every piece is examined under magnification. Simon Parfitt is the mammal specialist on the AHOB team. A paleontologist at the Natural History Museum and University College London, Parfitt has spent decades identifying fragmentary fossil bones. His work is crucial because at Happisburgh, the bones of extinct animals provide the primary method of dating the site. Carbon dating doesn't work this far back in time. The technique is effective only to about 50,000 years. For older sites, archaeologists must use other methods. At Happisburgh, 3 lines of evidence converge: the types of mammals preserved in the sediments, the magnetic signature of the deposits, and the geological context of the river channels themselves. Parfitt lifts a large tooth from the collection. It's a mammoth molar, still sharp-ridged after 800,000 years. This is Mammuthus meridionalis, the southern mammoth, a primitive form that predates the woolly mammoth by hundreds of thousands of years. The tooth is distinctive, The grinding surface consists of a series of enamel plates, widely spaced. Later, mammoths evolved thinner, more closely packed plates, an adaptation to eating tougher, more abrasive vegetation during ice ages. This spacing is a diagnostic feature. It places the sediment layer in a specific time frame, before 700,000 years ago. Another critical find is this: a tiny jaw, barely 2 centimeters long. It belonged to a water vole. In paleontology, voles are nicknamed the vole clock because different species evolved in succession, each with distinctive tooth patterns. This particular vole is Mimomys savini, a species that went extinct around 700,000 years ago. The assemblage includes other extinct mammals, an early form of bison, extinct horses, and this, a hyena coprolite. Fossilized feces. Chemical analysis reveals it contains bone fragments from large prey animals. Hyenas were present, scavenging or hunting the same animals that early humans would have relied on for food. The third dating method is paleomagnetism. Earth's magnetic field reverses polarity at irregular intervals, and these reversals are recorded in sediments. Iron minerals in the sediment align with the magnetic field at the time of deposition. The team extracted oriented samples and tested them. The results showed reversed polarity, meaning the sediments were deposited during a period when Earth's magnetic field was the opposite of today's. The last reversal before the present field began was the Brunhes-Matuyama boundary, dated to 780,000 years ago. The Happisburg sediments must predate that boundary. Chris Stringer is the director of the AHOB project and one of the world's leading experts on human evolution. He spent 40 years studying how humans spread across the globe. The discovery at Happisburg forced him to reconsider long-held assumptions. Previous models suggested early humans expanded out of Africa only when they developed sophisticated technology, controlled fire, warm clothing, complex shelters. Without these adaptations, the theory went, they couldn't survive in northern climates. The standard textbook narrative placed the earliest northern Europeans at around 500,000 years ago, coinciding with evidence of fire use and advanced tools. The sediments at Happisburg preserve an ancient river landscape. 900,000 years ago, this location lay 15 miles further inland than it does today. Two great rivers converged here: the Thames, which flowed north through Norfolk before turning east, and the Bytham, a now extinct river that drained the Midlands. Together, they formed a wide estuary, bordered by grassland and salt marsh. The surrounding hills were covered with coniferous forest, pine, and spruce. The climate was cool, but not glacial. Analysis of pollen grains and plant remains indicates temperatures similar to southern Scandinavia today. Summers reach 16 to 18 degrees Celsius. Winters drop to 0 or below. Beetles are extraordinarily sensitive climate indicators. Species have narrow temperature tolerances, and their hard exoskeletons preserve well in sediments. The Happisburg deposits yielded remains of 160 species of insects, most of them beetles. By comparing the ancient species to modern distributions, researchers reconstructed the climate with remarkable precision. The assemblage indicates a temperate but cooling environment. Winter frosts were regular. This was not the Mediterranean warmth that humans typically inhabited. This was a challenging, marginal habitat. The animal community was diverse. Mammoths grazed the grasslands, horses and bison moved in herds, red deer and giant deer browsed at the forest edge. In the rivers, beavers built dams. Hippopotamus, yes, hippos wallowed in the slower channels, a reminder that even in a cooling climate, pockets of warmth persisted. But there were predators. Saber-toothed cats hunted in the forests. Cave lions prowled the grasslands. Striped hyenas scavenged kills. For a small hominin band, survival here would have required constant vigilance. They were not apex predators. They were potential prey. Between 2005 and 2010, the team recovered 78 flint artifacts from the Happisburg sediments. These are simple tools: cores, flakes, and retouched pieces. No hand axes. No sophisticated bifacial tools. This is Mode 1 technology, the most basic stoneworking tradition. The flakes show clear signs of intentional manufacture. There's the bulb of percussion, the characteristic swelling where the hammerstone struck. There are ripple marks radiating from the impact point. Some flakes have been further modified, with tiny chips removed from one edge to create a cutting surface. This particular flake is the one they nicknamed the butter knife. It's about 8 centimeters long, with one edge carefully retouched to create a straight, sharp blade. Under magnification, the wear patterns are visible microscopic striations consistent with cutting soft materials. Meat, perhaps. Hide. Plant fibers. The raw material is good quality flint from the local chalk. The hominins knew where to find it. how to test nodules for quality, how to strike them at precise angles. This wasn't random rock smashing. This was deliberate, skilled toolmaking that required knowledge passed down through generations. To understand what these tools could do, archaeologists conducted experiments. A skilled flint knapper recreated the Happisburg technology, producing cores and flakes using only hammerstone percussion. Then they tested the flakes on animal carcasses obtained from a butcher. The results were striking. Even these simple flakes could efficiently slice through hide, separate meat from bone, cut tendons and ligaments. A single flake remained sharp through the entire butchery of a deer-sized animal. For the Happisburg hominins, these tools would have been essential, the difference between eating and starving. Happisburg isn't a single site. It's a series of locations along the same stretch of coast, each representing a different time slice of the Cromer Forest Bed Formation. Site 3, with its 900,000-year-old tools, is the oldest. But Site 1, discovered earlier, dates to around 500,000 years ago. Site 1 yielded a much larger assemblage, over 2,000 flint artifacts, including hand axes. These are Mode 2 tools, more sophisticated than the simple flakes from Site 3. The difference illustrates technological change over 400,000 years. Human capabilities evolved, but the basic challenge surviving in this northern landscape remained. Before Happisburg, Boxgrove was Britain's oldest known archaeological site. In the 1980s and 90s, excavations there revealed a pristine, 500,000-year-old landscape. Thousands of flint tools, butchered animal bones, even a human shin bone, the earliest hominin fossil found in Britain. Boxgrove represented the conventional wisdom. Humans arrived in Britain during a warm interglacial period, when the climate was Mediterranean-like. They were big-game hunters, taking down horses, rhinos, and elephants. They had fire. They had sophisticated tools. Boxgrove fit the model. Happisburg demolishes that model. The people here were 300,000 years earlier. The technology was more primitive, the climate was harsher, and yet they survived for how long? We don't know. Perhaps just a few generations. Perhaps longer. The sediments suggest repeated visits over time, hinting at a landscape known to multiple groups. The question that haunts the researchers is simple. How? Without fire, how did they stay warm? Without substantial shelters, how did they survive the winter? Without advanced weapons, how did they defend themselves against predators? These questions push at the edges of what we understand about early human capabilities. Simon Lewis is the project's physical geographer. His role is to read the sediments to understand the sequence of deposition, the flow of ancient rivers, the formation of channels and flood deposits. At Happisburg, that's a complex puzzle. The site preserves multiple episodes of deposition. River channels cut and filled, estuarine muds accumulated during high tides, freshwater pools formed in backwaters, plant debris collected in quiet eddies. Each layer contains clues, pollen, seeds, wood fragments, insect parts that allow the team to reconstruct the environment with extraordinary detail. One layer yielded pine cones, perfectly preserved, down to the scales. Another contained seeds from aquatic plants, indicators of slow-moving, nutrient-rich water. Pollen grains, examined under high magnification, reveal the composition of the forests. Predominantly pine and spruce, with smaller amounts of oak, elm, and hazel. This isn't modern Britain. The plant community more closely resembles boreal forests of modern Scandinavia or Canada. It's a landscape adapted to short growing seasons, long winters, and periodic frost. For hominins used to the warmth of Africa or southern Europe, this would have been an alien, challenging world. The investigation didn't end with the excavation. Back in London, at the Natural History Museum, the real analysis began. Every fragment of bone, every flint flake, every seed and shell was cataloged, photographed, and examined by specialists. The museum's collections contain fossils from thousands of sites across Britain and Europe. By comparing the Happisburg material to these reference collections, the team could identify species, assess ages, and place the site in its broader context. This is the power of museum collections. They transform isolated finds into comprehensive understanding. Certain analyses require destructive sampling, removing tiny portions of specimens for chemical testing. One technique uses stable isotopes to reconstruct ancient diets and environments. Carbon and nitrogen isotopes in bone collagen reveal what animals were eating. Oxygen isotopes in tooth enamel record temperature and water sources. Unfortunately, the Happisburg sediments are too acidic for collagen preservation. The bones are fossilized, the original organic material replaced by minerals. But the geological sediments themselves contain isotopic signatures that provide climate data, confirming the beetle evidence. Winters were cold. In 2018, the investigation expanded offshore. Rachel Bino and a team from the University of Southampton used geophysical survey equipment to map the seabed beyond the beach. They were searching for submerged extensions of the Cromer Forest bed. The surveys revealed precisely that ancient sediments continuing beneath the North Sea. This may be the world's oldest underwater archaeological site. If tools and fossils exist in these submerged deposits, they're protected from the erosion that destroys the beach exposures. But accessing them requires complex diving operations. The diving team used specialized equipment to extract sediment cores from the seabed. Each core is a vertical column, preserving the sequence of deposits. Back in the lab, these cores are split lengthways and examined layer by layer. Some cores contain wood fragments, charcoal-like in appearance, but actually preserved by waterlogging. Others show the characteristic laminations of estuarine deposits, alternating layers of fine silt and coarser sand, recording the rhythm of tides 900,000 years ago. Not everyone accepts the Happisburg dates. Some archaeologists argue the flints could be geofacts, naturally broken stones that coincidentally resemble tools. Others question whether the geological dating is precise enough to support such extraordinary claims. At academic conferences, debates are heated. Skeptics point to the absence of human fossils. Without bones or teeth, how can we be certain humans were present? The flints could have been washed into the sediments from elsewhere. The association with the mammal fossils might be coincidental. The AHOB team anticipated these objections. They conducted detailed analysis comparing the Happisburg flints to naturally fractured stones. Flint can break in several ways: frost shattering, river transport, trampling by animals. Each process leaves distinctive patterns. True human-made tools show specific characteristics: directed force from a single impact point, precise angles of fracture, intentional retouch on edges. The Happisburg flints exhibit all these features. More importantly, they occur in concentrations patches where toolmaking occurred rather than scattered randomly through the sediments. The strongest evidence is contextual. The flints were found in organic-rich layers, associated with mammal bones, showing cut marks. They're not scattered throughout the deposits, but concentrated in specific layers' occupation horizons. The sediments around them are undisturbed, ruling out later intrusion. Professional archaeologists know the difference between artifacts and geofacts. Nick Ashton has excavated hundreds of Paleolithic sites. Simon Parfit has examined tens of thousands of fossils. These aren't amateurs making wishful interpretations. The evidence is solid. Some of the mammal bones from Happisburg show cut marks, fine scratches made by stone tools during butchery. Under scanning electron microscopy, these marks are unmistakable. They're V-shaped in cross-section, with parallel microstriations from the tool's edge. They occur in anatomically correct positions at joints where meat was removed, along bone shafts where periosteum was stripped. Natural processes, gnawing by carnivores, trampling, sediment abrasion, produce different marks. Tooth marks are U-shaped, with crushing at the edges. Trampling creates randomly oriented scratches. The Happisburg marks are consistent with systematic butchery by tool-using hominids. One crucial question remains unanswered. Did the Happisburg hominins have fire? The excavators looked carefully for evidence: charcoal, burned bone, heat-altered flint, scorched sediment. They found none. This absence is significant. At later sites, fire evidence is common. Boxgrove, at 500,000 years ago, has possible hearth features. Sites from 300,000 years onward show clear, repeated fire use. But at Happisburg, nothing. If fire was absent, the implications are profound. How do humans survive cold without fire? The researchers looked to recent human populations in similar environments. Arctic and subarctic peoples developed sophisticated clothing, built insulated shelters, and relied on high-fat diets for metabolic heat. But all of them had fire. Without fire, the Happisburg hominins would have needed extraordinary physiological adaptations or behavioral innovations we can't yet identify. Perhaps they migrated seasonally, leaving before winter's worst cold. Perhaps they had minimal clothing, animal hides draped over shoulders. Perhaps their metabolic rate was higher than ours, generating more body heat. These possibilities remain speculative. If the Happisburg tools weren't made by Homo heidelbergensis, who made them? The most likely candidate is Homo antecessor, pioneer man. This species is known from fossils found at Atapuerca in northern Spain, dated to around 800,000 years ago. Homo antecessor had a curious mix of features. The face was surprisingly modern, relatively flat, with small brow ridges. But the teeth and jaw were primitive, more like Homo erectus. Brain size was intermediate, around 1,000 cubic centimeters smaller than modern humans, but larger than Homo erectus. Between 1994 and 1996, Spanish archaeologists excavated over 80 fossils at Grandolina, representing at least 6 individuals. The remains showed evidence of defleshing cut marks on bones, percussion damage to extract marrow. The interpretation is grim. Cannibalism. Whether ritualistic or dietary, this evidence reveals a species capable of complex social decisions, tool use, and meat processing. Homo antecessor was not a primitive ape man. These were sophisticated hominins with behaviors we would recognize as fundamentally human. Ancient DNA analysis has revolutionized archaeology, allowing direct comparison between fossil humans. But at Happisburg, no human remains have been found. Without fossils, genetic analysis is impossible. The species identification rests on comparative anatomy with Atapuerca, geological age correlation, and artifact similarities. Even in Spain, DNA extraction from 800,000-year-old fossils has proved impossible. The organic material is too degraded. We may never know the genetic relationship between Homo antecessor and later humans. The fossils can tell us what they looked like, but not how they're related to us. One theory suggests that adapting to cold climates drove brain evolution. Surviving in variable, unpredictable environments requires cognitive flexibility, the ability to solve novel problems, transmit knowledge, and coordinate group activities. The Happisburg hominins face precisely these challenges. If this hypothesis is correct, the selective pressures of Northern Europe may have contributed to the evolutionary trajectory leading to modern humans. We are, in a sense, descendants of survivors, hominins, who pushed into marginal habitats and adapted through intelligence rather than physical strength. In May of 2013, a powerful spring storm struck the Norfolk coast. Waves undercut the cliffs at Happisburg, causing a massive collapse. Tons of sediment slumped onto the beach. When the storm passed, the foreshore was transformed, new layers of ancient sediment exposed at low tide. Martin Bates, a geoarchaeologist from the University of Wales, Trinity St. David, walked the beach the next day. In the intertidal zone, he noticed unusual surface textures, elongated depressions in the sediment. He photographed them, uncertain what they were. Back in his office, examining the images, realization struck. These might be footprints. The research team mobilized immediately. They had perhaps 2 weeks before tidal erosion would destroy the prints. Working during low tides, often in driving rain, they documented everything. Traditional molding techniques wouldn't work. The sediment was too soft, too waterlogged. Any attempt to cast the prints would destroy them. Instead, they used photogrammetry. Hundreds of overlapping photographs were taken from multiple angles. Computer software stitched these images into three-dimensional models, preserving every detail. The curve of arches, the impression of toes, the depth variations that recorded weight distribution. Isabelle de Groot is an expert in forensic anthropology and ancient footprints. She analyzed the digital models, comparing them to footprints made by modern humans, apes, and earlier hominins. The Happisburg prints are unambiguous. These are hominin feet. Approximately 50 impressions were identifiable across an area of 40 square meters. 12 were sufficiently complete for detailed analysis. 2 showed clear toe impressions, 5 toes forward-facing, with the big toe parallel to the others rather than divergent as in apes. The footprints ranged in length from 14 to 26 centimeters. Using the relationship between foot length and body height, approximately 15% in most human populations, de Groot estimated the heights of the individual. The smallest prints suggested a height of 90 centimeters, a young child, perhaps 3 or 4 years old. The largest indicated an adult of 1.7 meters, about 5'7". The size range represented at least 5 individuals, some children, some adults. The group composition suggested a family. The prints showed a directional trend. The group had been walking southward, upstream along the estuary margins. The spacing between prints varied, indicating different walking speeds. Some individuals had paused, creating deeper, more complete impressions. Others had walked quickly through, leaving only partial tracks. One sequence, clearer than the others, showed an adult and child walking close together. The child's footprints occasionally overlapped the adult's, suggesting they were holding hands or the child was following directly behind. This detail, trivial yet profound, humanizes the scene. These were not isolated hominids. This was a social group, moving through their landscape with purpose. The Happisburg footprints are remarkable, but they're not unique in the archaeological record. The most famous ancient footprints come from Laetoli in Tanzania, where 3.7 million years ago, Australopithecines walked across volcanic ash. Those prints revolutionized understanding of bipedalism, proving it evolved before large brains. Another site, Illoret in Kenya, preserved 1.5 million year old Homo erectus footprints. Those prints showed essentially modern foot anatomy: an arched foot, forward-facing toes, a push-off phase identical to modern walking. The Happisburg prints continue this record, extending it to northern Europe. The Happisburg prints existed for only 2 weeks. The sediment they were preserved in was soft, compacted silt exposed below the high tide mark. Every tide brought water surging across the surface, gradually eroding the prints away. By June of 2013, nothing remained, the surface scoured flat by currents. This transience is typical of soft sediment traces. The Laetoli prints survived only because volcanic ash quickly hardened and was then buried by another ashfall. The Illoret prints were in firm sand, rapidly covered by sediment. At Happisburg, there was no protecting burial. The erosion that exposed the prints also destroyed them. The photogrammetric models are now the only record. Each model consists of millions of data points, defining the three-dimensional shape of the print. Researchers can measure dimensions, analyze depth profiles, compare prints to each other, all without the original specimens. This technology has transformed archaeology. Sites that would once have been lost are now preserved digitally. The models can be shared globally, allowing multiple researchers to analyze the same evidence. They can be 3D printed, creating physical replicas for museum displays or teaching. The footprints were made in estuarine mud at the edge of the ancient Thames-Bitham river system. The hominins were walking along the shore, perhaps in the early morning. The tide was low, exposing mudflats. Behind them, grassland and forest stretched inland. Ahead, the river channel widened toward the estuary. Why were they there? The answer lies in the ecology of estuaries. These are rich environments: shellfish in the mud, fish in the shallows, birds nesting in the marsh grasses. For opportunistic foragers, estuaries provide abundant, easily accessed resources. The Happisburg group may have been collecting food. Later, archaeological sites show extensive use of shellfish. Middens, ancient garbage dumps, are piled with cockle shells, oyster shells, mussel shells. These humble resources provided reliable protein, required minimal technology to harvest, and were available year-round. At Happisburg, no shells were preserved, the acidic sediments dissolved them, but the ecological setting, mudflats, salt marsh, slow-flowing channels, would have supported the same species modern estuaries do. The hominins would have known this. Knowledge of food sources, transmitted between generations, would have been essential for survival. The footprints also reveal vulnerability. Walking in the open, along water margins, the group was exposed to predators. Saber-toothed cats preferred forest edge habitats. Lions hunted grasslands. Hyenas scavenged, but also killed. A family group with young children would have been easy targets. The absence of modern weapons, thrown spears, bows, atlatls, meant defense relied on vigilance, group cohesion, and perhaps fire. If these hominins lacked fire, as the evidence suggests, their survival strategies remain mysterious. Perhaps they took refuge in dense vegetation. Perhaps they climbed trees at night. Perhaps groups were larger than the 5 individuals represented in the footprints, providing collective defense. One possibility is seasonal occupation. Many animal species migrate to avoid harsh winters. Birds fly south. Caribou move to lower latitudes. Perhaps early humans did the same, moving into northern Europe during warmer months and retreating south as winter approached. This hypothesis explains the absence of cold weather adaptations. If hominins were only present from spring through autumn, they wouldn't need fire or sophisticated clothing. But it raises another question. Why make the journey? What resources in northern Europe were worth the risk and effort of traveling hundreds of kilometers? The answer may lie in resource predictability. In Africa and southern Europe, resources were abundant but competed for by dense hominin populations. Northern Europe, by contrast, was sparsely populated, perhaps even uninhabited for long periods. Game animals were plentiful. Plant resources, though seasonal, were unexploited. By moving north in summer, groups could access these resources without competition. The energetic cost of migration might have been offset by abundant food and reduced conflict with other groups. This strategy, seasonal ranging over vast territories, characterizes many modern hunter-gatherer societies. Another theory suggests periodic extinctions and recolonizations. Climate in Europe fluctuated wildly during the Pleistocene. Warm interglacials alternated with glacial periods. During cold phases, ice sheets covered much of northern Europe. Humans couldn't survive. Populations died out or retreated south. When climate warmed, new groups moved north, pioneering expeditions testing the limits of the habitable zone. Most attempts may have failed. The Happisburg hominins might have been one such failed experiment, a group that survived for a few generations but eventually succumbed to cold or predation or disease. The Happisburg discoveries fit into a broader pattern. Human occupation of northern Europe was sporadic, episodic, tied to climate cycles. Sites cluster in warm periods and disappear during cold phases. This pattern persists for hundreds of thousands of years. Around 700,000 years ago, at Pakefield in Suffolk, another group left stone tools and cut-marked bones. 500,000 years ago, the Boxgrove hominins hunted horses and made beautiful hand axes. 300,000 years ago, sites multiply across Britain and continental Europe. By 250,000 years ago, Neanderthals fully adapted to cold dominated the region. Where does Happisburg fit in this story? It represents the earliest wave, the first tentative probing into a hostile environment. These weren't the ancestors of Europeans. They were pioneers who didn't survive. Genetic dead ends. Evolutionary experiments that failed. But they demonstrate something crucial. Early hominins were capable of far more than scientists previously believed. The traditional narrative emphasized physical adaptation, thicker bodies, different metabolisms, biological changes allowing cold tolerance. Happisburg suggests another possibility: behavioral flexibility. Even primitive hominins could survive in marginal habitats through intelligence, cooperation, and cultural transmission of knowledge. This has implications for understanding cognitive evolution. If hominins 900,000 years ago were smart enough to survive in northern Europe, when did that intelligence emerge? What selective pressures drove its development? And what does it tell us about the relationship between brain size and behavior? Homo antecessor had a brain about 70% the size of modern humans, yet they made stone tools, butchered animals, possibly communicated through language, and solved complex ecological problems. Brain size alone doesn't determine intelligence. Organization, connectivity, efficiency, these matter more. The stone tools from Happisburg are simple, but simplicity doesn't mean stupidity. These Mode 1 tools, cores, and flakes serve their purpose effectively. They could butcher a carcass, process plant materials, work wood. For small, mobile groups, carrying minimal equipment, simple tools made sense. More complex tools, hand axes, spear points, blade technologies developed later, in response to different ecological pressures or social contexts. At Happisburg, with resources scattered across a vast landscape, efficiency mattered more than elegance. A sharp flake, quickly made, was better than an elaborately crafted tool that took hours to produce. Did the Happisburg hominins have language? No, direct evidence survives. But their behavior implies some form of communication. Coordinating group movement, teaching tool making, sharing knowledge of resources all require information transfer beyond gestures. Modern studies of Homo antecessor skull anatomy suggest they had the ear structures necessary for perceiving human speech sounds. Whether they could produce complex vocalizations is unknown. The fossil record preserves bones, but not soft tissue. The debate over language origins remains unresolved. The footprints offer a rare glimpse of social structure. The size range, adults and children together, suggests nuclear families or extended kin groups. This pattern is universal in modern humans, but harder to document in early hominins, where evidence usually consists of scattered bones and tools. Parental care, necessary for raising large-brained offspring with extended childhoods, would have been well established by 900,000 years ago. The Happisburg group probably traveled together, foraged together, and protected each other. Children learned by watching adults, acquiring skills essential for survival. In February of 2014, the Natural History Museum opened a major exhibition showcasing the Happisburg discoveries. The footprint photogrammetry models were displayed, alongside the flint tools and fossil mammals. For the public, this was the first chance to see the oldest evidence of humans in northern Europe. The exhibition attracted massive crowds. People stood in front of the footprint display, marveling that they were looking at traces left by a family who walked this beach nearly 1 million years ago. The human connection transcended the vast time gap. These weren't abstract hominins. They were individuals, a child walking with an adult, leaving impressions that survived for one fleeting moment before being erased by the tides. The Happisburg investigation continues. Coastal erosion proceeds relentlessly, exposing new sediments each winter. The research team established a monitoring program, training local volunteers to survey the beach and report discoveries. Since 2013, nearly 2,000 additional flint artifacts and fossil bones have been recovered by members of the public. Each find adds to the picture. Some represent new time periods, episodes of occupation not previously documented. Others extend the geographic range, revealing that hominins were present along the entire East Anglian coast. This collaboration between professionals and amateurs is increasingly common in archaeology. Sites are discovered faster than researchers can excavate them. Trained volunteers, fossil collectors, metal detectorists, local historians provide invaluable assistance, finding sites and reporting them to authorities. At Happisburg, collectors like Paul Durbridge and Bob Much made crucial early finds that attracted professional attention. Without their observations, Site 3 might have eroded away unnoticed. Citizen science democratizes archaeology, involving communities in the investigation of their own history. Ironically, the same erosion that reveals these ancient sites also destroys them. As sea levels rise and storms intensify, coastal erosion accelerates. Within decades, much of the Happisburg cliff section will have collapsed into the sea. Sites will be lost before they can be excavated. This is a global crisis. Archaeological sites worldwide face destruction from development, agriculture, looting, and environmental change. At Happisburg, the threat is imminent. The strategy now is damage control, document everything, recover what can be saved, and accept that some evidence will be lost forever. The offshore surveys offer hope. If significant deposits exist beneath the seabed, protected from wave action, they may survive longer. Underwater excavation is technically challenging and expensive, but it's becoming more feasible as technology advances. Remote-operated vehicles can map sites at depths impossible for divers. Sediment sampling devices can extract cores without disturbing surrounding deposits. Underwater photography and photogrammetry allow documentation comparable to terrestrial excavations. Happisburg may become one of the first Paleolithic underwater archaeological sites systematically investigated. Standing on the beach at Happisburg today, looking out across the North Sea, it's hard to imagine what this landscape was like 900,000 years ago. The river is gone, replaced by ocean. The forests are gone, replaced by fields and villages. The megafauna are extinct. The hominins who walked here left no descendants, at least not directly. Yet, they were here. The evidence is undeniable. Flint tools, made by skilled hands. Footprints, preserving one moment in the lives of a family. Butchered bones, recording meals consumed. These fragments, rescued from eroding cliffs and rising tides, tell a story that rewrites human history. Chris Stringer has spent his career studying human origins, but Happisburg surprised even him. The conventional wisdom that Northern Europe was beyond early hominin capabilities has been overturned. The boundary of the possible has shifted. What Happisburg shows us, Stringer reflects, is that we've consistently underestimated our ancestors. Every time we think we've defined the limits of what early humans could do, we find evidence that pushes those limits further. These hominins were tougher, smarter, more adaptable than we gave them credit for. For Nick Ashton, Happisburg has been a decade-long commitment. Winters spent excavating in freezing rain, summers analyzing finds, years writing grant proposals and research papers. The work is painstaking, often frustrating, occasionally rewarding. The thing about archaeology, Ashton says, is that you're always working with incomplete evidence. We'll never know everything about these people. We'll never find their skeletons. We'll never hear their language. But every flint flake, every footprint, every cut-marked bone, they're messages from the deep past. Our job is to read those messages as accurately as we can. The discoveries at Happisburg have implications beyond archaeology. They speak to fundamental questions about human nature. What makes us human? Intelligence? Tool use? Language? Social cooperation? The Happisburg hominins had all these things in simpler forms, perhaps, but recognizably present. They were us. Not genetically, they were a different species. But behaviorally, cognitively, emotionally, the difference is narrow. They cared for their children. They worked together. They solved problems. They adapted to challenges. In these traits, we see the foundations of humanity emerging nearly a million years ago. Many questions remain. Who were these hominins? How long did they survive in Britain? Did they have fire, clothing, shelters, things that might not preserve archaeologically? What became of them when climate deteriorated? Were they ancestors of later Europeans, or an evolutionary dead end? Future discoveries may answer some questions. A hominin fossil from Happisburg would transform understanding, allowing direct species identification and perhaps even DNA analysis. More footprint sites might reveal group sizes, age distributions, seasonal patterns. Offshore excavations could uncover preservation conditions impossible on the eroding beach. Archaeological methods improve constantly. Techniques that didn't exist 20 years ago are now standard. Photogrammetry transformed the footprint documentation. Paleomagnetic dating allowed precise age determination. Stable isotope analysis reveals ancient diets and climates. Future technologies, perhaps ground-penetrating radar that can detect flint artifacts beneath sediment, perhaps ancient protein analysis that works when DNA fails, will enable investigations impossible today. Happisburg will continue to yield discoveries as long as the cliffs continue to erode and archaeologists continue to look. The Happisburg discoveries depended on luck, the right storms exposing the right layers at the right time, the right people walking the beach and recognizing what they saw. But luck alone isn't enough. You need trained observers who know what to look for. You need funding to support excavations. You need specialists who can analyze the finds. Archaeology is preparation meeting opportunity. The AHOB project existed because decades earlier, Chris Stringer convinced the Leverhulme Trust that understanding human occupation of Britain was scientifically important. That funding allowed Nick Ashton to monitor the Norfolk coast. That monitoring meant being present when erosion exposed the Happisburg deposits. Britain is just one piece of the human expansion story. Similar processes played out globally. Hominins spread from Africa into Asia before 2 million years ago. They reached Europe by at least 1.4 million years ago. They adapted to deserts, mountains, rainforests, Arctic tundra. Each environment presented unique challenges. Each required innovations. The cumulative effect was a species, our species, Homo sapiens, that could live anywhere on Earth. We inherited that adaptability from ancient ancestors, like those who walked the beaches of Happisburg. The Happisburg hominins probably didn't survive. Climatic deterioration around 800,000 years ago coincided with glacial expansion. Ice sheets advanced across northern Europe. Hominin sites disappear from the archaeological record. The region was abandoned, perhaps for 100,000 years or more. Later, new groups arrived. Some survived longer. Eventually, Neanderthals evolved full cold adaptations and thrived in Ice Age Europe. Then, 40,000 years ago, modern humans arrived and Neanderthals vanished. The story is one of repeated colonizations, extinctions, replacements, a dynamic process still not fully understood. Did the Happisburg hominins leave any legacy? Not genetic, they were almost certainly an evolutionary dead end. But they proved something important, that hominin expansion was driven not by physical adaptation, but by behavioral flexibility. Intelligence, transmitted culturally rather than genetically, allowed survival in environments where biology alone would fail. This is humanity's defining trait. We don't wait for evolution to adapt us to new environments. We invent solutions, tools, clothing, fire, shelters, social structures. That capacity emerged deep in our evolutionary history, visible even in the primitive technology preserved at Happisburg. The Happisburg flint tools and footprint casts are now permanently displayed at the British Museum. Visitors from around the world examine them, trying to grasp the vast timescales involved. 900,000 years. 450 times as long as recorded history. 30,000 human generations. Yet the connection feels immediate. A child's footprint, preserved in mud. A cutting tool, made by someone's hands. These are tangible links to the deep past, more evocative than any written text could be. They remind us that archaeology isn't just about dates and classifications, it's about people. The Happisburg discoveries are now taught in schools and universities worldwide. Textbooks have been revised to reflect the new, earliest date for human occupation of Britain. The site appears in documentaries, books, and museum exhibits. A generation of students is learning that human capabilities were far greater than previously believed. This dissemination takes time. Academic papers appeared between 2010 and 2014. Popular books and documentaries followed. Now, Over a decade later, the knowledge is filtered into mainstream education. That's how science progresses: discovery, verification, dissemination, incorporation into consensus. Happisburg isn't alone. Other early sites across Europe tell similar stories. Dmanisi in Georgia preserved 1.8 million-year-old fossils and tools, the earliest hominins outside Africa. Atapuerca in Spain yielded 800,000-year-old Homo antecessor remains. These sites collectively document the slow, episodic expansion of humans across continents. Each site contributes unique information. Dmanisi preserved complete skulls, allowing detailed anatomical study. Atapuerca had exceptional preservation, including possible evidence of cannibalism. Happisburg provides the environmental context, proof that hominins could survive in suboptimal, challenging habitats. Together, the sites create a comprehensive picture. The Happisburg investigation exemplifies modern archaeology, profoundly interdisciplinary, requiring expertise in geology, paleontology, anthropology, chemistry, physics, and more. No single person commands all necessary skills. Success depends on collaboration. The AHOB project brought together 50 researchers from multiple institutions. Geologists dated the sediments, paleontologists identified the fossils, archaeologists analyzed the tools, paleobotanists examined plant remains. Each contribution was essential. This is how complex questions are answered, through teamwork, shared data, and mutual respect across disciplines. The Happisburg site will continue to erode. In 50 years, much of the current cliff section will be gone. But erosion also exposes new deposits. The monitoring program ensures that discoveries don't go unnoticed. Each winter, after storms, volunteers survey the beach. Each find is reported, recorded, and, if significant, excavated by professionals. This reactive approach, responding to erosion rather than conducting planned excavations, is necessary given the site's nature. Planned excavations aren't possible when the site exists only at low tide and may disappear within days. Instead, archaeologists must be ready to mobilize quickly when something important appears. The climate analysis from Happisburg provides an exceptionally detailed reconstruction of conditions 900,000 years ago. Multiple lines of evidence, beetle assemblages, pollen spectra, plant macrofossils, sedimentary structures, mammal fauna converge on a consistent picture. This was a cool, temperate climate, transitioning toward glacial conditions. Summers were slightly warmer than today's Britain, reaching 18 degrees Celsius. Winters were colder, dropping to -3 degrees. The landscape was a mosaic of coniferous forest, grassland, and wetlands. Seasonality was pronounced, with short summers and long, dark winters. Modern Britain is densely populated, heavily urbanized, intensively farmed. 900,000 years ago, the human population numbered perhaps a few dozen individuals across the entire region, maybe fewer. Population density was measured in persons per 1,000 square kilometers. This emptiness is hard to imagine. No roads, no buildings, no fields. Just wilderness forest, grassland, river channels, teeming with wildlife. The Happisburg hominins were a tiny presence in an immense landscape, struggling to survive against overwhelming odds. Where does Happisburg rank among archaeological discoveries? It's not as visually spectacular as Pompeii, not as rich as King Tut's tomb. But in terms of scientific importance, it's transformative. It pushed the boundary of the known by 300,000 years. It challenged fundamental assumptions about early human capabilities. Discoveries like this are rare, perhaps one per decade redefines a major aspect of human history. Happisburg did that. It will be discussed in textbooks a century from now. Just as we still discuss Lucy, the Australopithecine skeleton discovered in 1974, or the Laetoli footprints discovered in 1976. Behind every archaeological discovery are people, researchers who dedicate careers to painstaking work, volunteers who give their time freely, and funding agencies that take risks on uncertain outcomes. Nick Ashton spent 15 years monitoring the Norfolk coast. Chris Stringer built a career on human evolution, culminating in directing the AHOB project. These aren't just abstract scientists. They're individuals with families, mortgages, frustrations, and triumphs. They work in miserable conditions, cold, wet, exhausted, because they're driven by curiosity about the past. Their dedication makes discoveries like Happisburg possible. The tide is coming in. Water surges across the foreshore, erasing footprints left by today's visitors just as it erased those left 900,000 years ago. In the distance, the lighthouse stands a marker of human permanence in a landscape of constant change. The Happisburg hominins lived briefly, struggled constantly, and vanished without leaving descendants. But they proved something important: that humans, even in their most ancient forms, possess the cognitive flexibility and behavioral adaptability that would eventually allow our species to dominate the planet. They were pioneers, explorers, survivors. They walked this beach when Britain was young, and through archaeology, through the patient recovery of stone tools and fossilized footprints, we can still hear their story echoing across the millennia.